在汉斯·贝特于1938年发表太阳的光和热系来自氢的核融合后，欧美等已开发国家为了使用干净、安全且无匮乏疑虑的能源，都早已从20世纪中叶开始投入核融合反应的研究。目前研究核融合的机构主要为美国的国家点燃实验设施和跨国合作的国际热核融合实验反应炉，分别以惯性约束核融合和磁约束核融合的方法进行研究。但直到现在，国家点燃实验设施和跨国合作的国际热核融合实验反应炉还只是处在实验和摸索阶段。核融合反应可能是星际旅行最具高能量效益的来源，如能开发出此种能源并将其应用在太空船上，星际旅行极有可能美梦成真。这部影片是一系列有关星际旅行的第二部，也是旨在凸显星际旅行的困难度。为了解决火力发电厂所产生的二氧化碳和其他大气污染物，以及核分裂发电所产生的辐射污染和核废料存放问题，寻找洁净和无使用匮乏疑虑的替代能源是地球刻不容缓的课题。水力、风力和太阳能等发电方式虽都已在使用中，但在效能和成本考量下，都不是最佳选择。因此，欧美等已开发国家都早已在汉斯·贝特于1938年发表太阳的光和热系来自氢的核融合后，即从20世纪中叶开始着手和融合反应的研究。为了产生核融合反应，必须将气体加热以增加碰撞频率。当温度达数千万度 C 时，电子会在碰撞之际从原子剥离。在这种极高温下，剥离的电子和裸露出的原子核会以电浆，亦称离子体状态存在。科学家从能量的角度选择利用氢的同位素刀，穿在极高温下结合生成重元素氦四和中子，并释放出如同持续发光发热的太阳能的巨大能量。刀穿核融合反应被认为在最低温度下能产生最高能量效益的核融合反应。刀和氚都是氢的重同位素，因其高中子质子比，使得它们的融合具有低能胀。原子核内中性中子的存在有助于透过合力将它们拉在一起，而带正电的质子的存在则会透过静电力将原子核推离。增加质子或移去中子均会增加能胀。刀核含有一个质子和一个中子，是大爆炸过程中产生的，不具放射性，也没有毒性。在地球，刀可直接取自海水，来源不予匮乏，可说是最理想的能源取得方式。氚含有一个质子和两个中子，具有放射性，通过贝塔衰变变为氦三，半衰期为12.32年，另放出高速移动的电子。除非大量吸入氚才会对人体有害，自然界存在少量氚。当宇宙射线撞击到刀时，刀和中子会结合为氚，因此氚也可借由在核融合反应本身产生的中子来生成。但由于刀和氚核子均带正电，会互相排斥，即使在热且致密的太阳中心，质子在融合之前平均会存在数十亿年。因此，对于实际核融合发电系统，由于电浆的密度非常低，约为大气密度的10万分之一，反应速率必须显著增加才符合需求和效益，而这需要加热到上亿度。劳森于1957年发表劳森准则，定义了核融合反应炉达到点火所需的条件，以及利用核融合反应所产生的热来持续加热电浆，在部分热能逃逸到外部且不需再输入外部能量的情况下，仍足以维持电浆的温度。这个条件涉及到电浆的温度、密度和热能的局限时间。而由这三种条件所形成的三重积不等是有一个最小的需求值，在地球上要满足劳森准则是非常困难的。这就解释了为什么核融合研究已经花了超过半世纪那么久的时间，到现在还无法实际应用到工业上。如果将来这项技术能够成功，1加仑海水能提供相当于300加仑汽油的能源，而50杯水燃料含有相当于2吨煤炭的能量。目前研究核融合的机构主要为美国的国家点燃实验设施和跨国合作的国际热核融合实验反应炉，分别以惯性约束核融合和磁约束核融合的方法进行研究。位于美国加州劳伦斯利弗莫尔国家实验室的国家点燃实验设施是以雷射束加热内含刀和氚的燃料球的外层，被加热的外层往外爆炸时，会产生一个反作用力，加速向内压缩燃料球，借由这个过程所产生的冲击波，加温加压在中心处的燃料，使其产生核融合反应以达到点燃的条件。接着借由链锁反应进行后续的大部分融合反应。国家点燃实验设施于2013年10月初发布突破重大里程碑的消息。新闻稿指出，他们利用光放大器将一束雷射分裂成192道光束，并聚焦于中央一个直径0.5毫米含刀氚燃料的胶囊，成功的让核融合反应释出的能量超过燃料球消耗的能量。但要符合经济效益，释出和消耗的能量需达到一定比例，且必须是可受控的。2022年12月5日，国家点燃实验设施创造了科学史，国家点燃实验设施首次实现点燃及科学损益平衡，与输入能源相比，实现了154%的能源产量， 这是劳伦斯利弗莫尔国家实验室60多年来雷射驱动惯性约束核聚变研究和开发的顶峰。然而，虽然这在科学上是成功的，但实验产生的能量还不到该设施用于创造它的能量的1%。虽然核聚变产生的能量 3.15 mJ 比传递到聚变目标的雷射能量 2.05 mJ 更多，但提供 2.05 mJ 能量的雷射在该设施中需要大约300 mJ 才能生产。12月的实验之后又进行了4次点燃，分别为2023年7月30日、2023年10月8日、2023年10月30日和2024年2月12日。虽然最后一次的实验估计产生了 5.2 mJ， 是输入能量 2.2 mJ 的2倍以上，但离成功还很遥远。国际热核融合实验反应炉是一种使用磁力线约束电将悬浮在反应炉中来产生聚变能的方法，被认为比国家点燃实验设施更有成功的机会。2006年5月24日，欧盟、美国、中国、日本、韩国、俄罗斯和印度7方代表草签了一系列相关合作协议，拟规划建造一座国际热核融合实验反应炉，简称为 ITER， 以执行托卡马克 （Tokamak） 试验来验证全尺寸可控核融合技术的可行性，将不会实际用来发电。托卡马克又称环磁机，由苏联所研发，是一种结合环相场和极相场将电浆封闭在内来实现磁约束融合的环形容器。Tokamak 这个名字乃取环形 （toroidal） 真空室 （camera） 磁 （magnet） 线圈 （kotaska） 4个字的前2个字母所组合而成。2006年11月21日，7个成员国正式同意资助建造核融合反应炉，地点选在法国普罗旺斯、阿尔卑斯、蓝色海岸南部的卡达拉舍。为了让核融合反应炉产生较高的输出功率，电浆必须长时间保持在高温、高密度状态。国际热核融合实验反应炉因此被设计成高度和直径都为30公尺的巨大装置，预计耗资约50亿欧元的经费。国际热核融合实验反应炉的既定预计目标是展示工业规模核聚变所需整合的系统类型，以实现称为 Q 大于等于10的科学基准，或将50兆瓦的加热功率输入到电浆，而从机器中输出500兆瓦的聚变功率。犹如国际热核融合实验反应炉大脑和中枢神经系统的自动控制系统将于2024年末准备就绪，并开始系统整合调试。国际热核融合实验反应炉原预划于2025年12月启动氢的电浆实验，这一重要的里程碑将标志着建设阶段的结束和运营的过渡。在系统逐年升级后，2035年即会开始进行实际燃料刀穿的核融合实验，整个实验预计花10年左右完成，但由于 COVID-19 疫情、施工不当以及法国和监管机构因担心现场辐射问题而要求暂停建设，而造成整个计划时程延宕和成本增加。结果是，国际热核融合实验反应炉计划的最后阶段，刀穿燃料的聚变反应，从2035年被推迟到2039年，而成本将超过220亿美元，约为最初估计的4倍。国际热核融合实验反应炉托卡马克将利用中性粒子射束、离子回旋加热和电子回旋加热3种外部加热来源协同工作，以提供50兆瓦的输入加热功率，以加热840立方米反应是中约 0.5 公克刀焊穿的混合气体至核融合所需温度。核融合反应预计产生500兆瓦的热输出功率，且持续达1000秒。为了达到核融合反应的输出功率为输入功率的10倍以上的设计目的，国际热核融合实验反应炉使用超导体作为电磁铁线圈的材料，以大幅降低电能的耗损。而为了让真空式的稀薄气体达到电浆状态并产生核融合反应，国际热核融合实验反应炉托卡马克内的温度必须高达摄氏 1.5 亿度或太阳核心温度的10倍，没有任何容器可以承受这么高的温度。国际热核融合实验反应炉特别设计了一个可以让电浆悬浮且不会碰触到炉壁的磁场系统。国际热核融合实验反应炉磁场系统包括18个超导环相场和6个极相场或称垂环场线圈，一个中央螺线管，以及一组校正线圈，用磁场约束、形塑和控制真空容器内的电浆。18个环相场的磁铁排成甜甜圈状，产生围绕环面的磁力线，其主要功能是约束电浆粒子。极相场线圈系统由安置在环形磁铁结构外的6个水平的独立线圈组成，产生垂直环面绵延不断的环形磁力线。极相场磁铁会挤压电，将使其远离炉壁，并以这种方式来保持电浆的形状和稳定性。中央螺线管线圈是磁铁系统的骨干，本质上是一个大的变压器，借由改变流经线圈的电流以获得与移动磁铁相同的效果，再与其垂直的电浆流动的环面感应出电流，同样会产生极相场。环面磁力线和垂环磁力线一起作用，会在真空容器内的环形式或环面产生不断螺旋绕转且稳定的甜甜圈状磁力线，并将电浆陷在磁力线内，使其不会碰触到炉壁。 核融合反应生成的氦原子核被束缚在电浆中，而中子流则会四处飞窜而不断高速撞击覆盖在真空容器内表面的中子缓冲层，在动能被缓冲层吸收并转换成热能后减慢下来。缓冲层内部的冷却水系统被设计用来将距离 1.5 亿度 C 的电将仅几公尺远的真空容器内表面降温至约240度 C。但冷却水却也因此会被加热，这个被加热的冷却水在将来工业用的核融合发电厂会被用来加热另一个系统的水，以产生水蒸气来驱动涡轮机，进而带动巨大电磁铁转动以产生电流，就跟现在的发电厂运作的机制一样。以核融合反应来产生电力，是地球人类目前最大的梦想，但国家点燃实验设施和国际热核融合实验反应炉现在还只是处在实验和摸索阶段，想要利用和享用和融合反应所产生的干净和安全能源，显然还有一段相当漫长的路要走。诚如国际热核融合实验反应炉主任彼得罗·巴拉巴斯基在计划延迟的新闻发布会上解释延误的原因时，还特别强调，规划过于乐观，期盼能早日以核融合反应来发电恐不切实际。
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low-energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switchyard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10mm target assembly called a hole-ron, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
Welcome back to Tech Curiosity, where we delve into the innovations shaping our future. Today, we're talking about a giant leap in energy technology, the world's largest nuclear fusion reactor. This isn't just any reactor, it's the epitome of human ingenuity and a beacon of hope for a cleaner, sustainable energy future. So, let's ignite our curiosity and explore this marvel of modern science. Nuclear fusion, the process that powers the sun, has long tantalized scientists with its promise of a near-limitless source of clean energy. Achieving this on Earth has been a challenge that has sparked decades of research. Now, the fruits of that labor are materializing in the form of the world's largest nuclear fusion reactor, an engineering masterpiece that could change the course of our energy history. To appreciate the significance of this reactor, let's first understand nuclear fusion. It's the process of combining 2 light atomic nuclei to form a heavier nucleus, releasing an immense amount of energy in the process. Unlike nuclear fission, which splits atoms and is used in current nuclear power plants, fusion offers a cleaner alternative, with water as its primary byproduct, thus eliminating the long-lived radioactive waste challenge. The quest for controlled fusion on Earth has led to the development of the tokamak, a donut-shaped chamber where magnetic fields confine superheated plasma, allowing fusion to occur. This requires the plasma to reach temperatures exceeding those at the center of the Sun, a feat that is as challenging as it sounds. Enter ITER, the International Thermo Nuclear Experimental Reactor. Nestled in the countryside of southern France, ITER is the world's largest fusion experiment. A collaboration among 35 nations, ITER is designed to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. ITER's tokamak is an engineering giant, with a central solenoid coil towering over a multi-story building and a vacuum chamber where fusion will occur, large enough to fit a 3-story house. The numbers are staggering. It's expected to produce 500 megawatts of output power from only 50 megawatts of input power, achieving the coveted goal of energy gain, or Q10, for the first time in history. The engineering that goes into ITER is groundbreaking. Its superconducting magnets are the largest and most powerful ever built, designed to withstand the incredible forces and temperatures of the plasma. The reactor's walls are lined with beryllium and tungsten, materials chosen for their high melting points and durability. In the heart of the tokamak, the plasma will be heated to over 150 million degrees Celsius, 10 times hotter than the core of the Sun. This requires an orchestra of advanced technologies, from radio frequency heating to neutral beam injectors, all working in unison to ignite and sustain the fusion reaction. The road to achieving fusion energy is long and complex. ITER's construction began in 2013 and is set to complete by 2025, with the first plasma expected shortly after. The project serves as a proof of concept, paving the way for the first fusion power plants that could be operational as early as the 2040s. This timeline is crucial as the world grapples with climate change and the urgent need for sustainable energy solutions. Fusion energy holds the promise of being an inexhaustible, safe, and environmentally responsible power source, potentially revolutionizing the way we power our planet. Despite the optimism, the path to fusion energy is not without challenges and criticisms. The immense cost, over $22 billion for ITER alone, and the lengthy development time are points of contention. Critics argue that the resources might be better spent on immediate and more certain renewable technologies like wind and solar. Yet, proponents of fusion counter that the potential benefits outweigh the costs and risks. Fusion offers a baseload power source without the intermittency issues of current renewables, making it a critical part of a diversified energy future. As we wrap up our exploration into the world's largest nuclear fusion reactor, we stand on the precipice of a new energy dawn. ITER is a testament to international cooperation and the relentless pursuit of a dream that has been decades in the making. Stay tuned to Tech Curiosity for more updates on this fascinating journey. If you're excited about the future of energy, make sure to hit the like button, subscribe, and turn on notifications for more tech deep dives. See you in the next one.